Hello and welcome to this new video series in which we will look at different methods for solving system of linear equations. We'll be using Python code snippets for visualization and to show how these methods work. Let's say we have a system of equations comprising of m equations and n unknowns or parameters. We can write this system in a matrix vector form where A is an m by n coefficient matrix, x is a parameter vector of size n by 1, and B is an m by 1 output vector. Now let's look at three different cases based on the number of equations and the number of unknowns. The first case is a square matrix where number of equations equals number of unknowns. In the second case, we have an underdetermined system as the number of equations is smaller than the number of unknowns. In the last case, we have an overdetermined system as it has more equations than unknowns. When the coefficient matrix is square and non-singular, that is, its determinant is non-zero and it is full rank, then we can get a unique solution using the product of A inverse and the output vector B. In the underdetermined case, we have many solutions and we can find a minimum norm solution using this equation. In the overdetermined case, there might exist no exact solution and we must find a solution based on global error minimization. Let's look at an example. We want to solve this system comprising two equations and two unknowns. We can write this system into matrix vector form and we can easily compute and see that the determinant of A is non-zero. For a 2 by 2 matrix, determinant is calculated by subtracting the product of off-diagonal elements from the product of diagonal elements. And if the determinant is non-zero, a 2 by 2 matrix is full rank, that is, its rank is equal to 2. In the previous slide, we have seen if a coefficient matrix is non-singular and full rank, we can find a unique solution of the system by multiplying the inverse of A with the output vector, which leads to a solution where x1 is 3 and x2 is equal to 4. Let's try to visualize this system of equations, and we can see that these represent different lines. We can convert these to a familiar slope-intercept form, which is y is equal to mx plus c. And if we plot these two lines, we can see one has a positive slope and the other has a negative slope. The point where these two lines intersect is the unique solution where x1 is equal to 3 and x2 is equal to 4. This is the function we use to plot a line. It takes x, m, and c as arguments. We then calculate y values using the slope-intercept formula and then plot x and y values as a line. And this is the code which we use to plot both lines in the same figure. In real applications, we may encounter much larger and sparse matrices. Computing the generalized inverse might be a challenge due to high computational cost and memory requirements. In the coming videos, we'll look at multiple direct and iterative methods in more detail. We'll write and discuss Python codes for these methods and we'll use those codes to solve this curve fitting problem, in which we will find the unique quadratic equation of the form y is equal to ax squared plus bx plus c, whose graph passes through these 3 points, minus 220, 15, and 325. Thanks for watching this video. I hope you liked it. Please subscribe and see you in the next video where we will discuss the Gauss elimination method in more detail.